Hello everyone. In this class, we'll try to understand what is gas exchange in the lungs. Coming to the physics involved in the gas diffusion, the gases are simple molecules that are free to move among one another by diffusion. The energy for movement of molecules in diffusion is provided by kinetic motion of the molecules themselves. For free molecules are at linear movement at high velocity and strike other. Then they bounce away in a new direction and continue until striking the other molecules again. In this way, the molecules move rapidly and randomly among one another. In a solution having a high concentration of particular gas at one end and low concentration at other end, the net diffusion of gas will occur from the area of high concentration towards the area of low concentration. Though the random movement of molecules occur in both directions, the rates of diffusion in each of the two directions are proportionately different. Finally, the net diffusion in the direction of the concentration gradient occurs. The pressure is caused by multiple impacts of moving molecules against a surface. Therefore, pressure of a gas acting on the surfaces of the respiratory passages and alveoli is proportional to the summated force of impact of all the molecules of that gas striking the surface at any given instant. Thus, pressure is directly proportional to the concentration of gas molecules. Air in atmosphere is a mixture of gases, mainly the oxygen, nitrogen, and carbon dioxide. The rate of diffusion of each of these gases is directly proportional to the pressure caused by that gas alone, which is called as partial pressure of that gas. In air, 79% is nitrogen and 21% is oxygen. The total pressure of this mixture at sea level averages about 760 mm of Hg. At each gas, as each gas contributes to the total pressure in direct proportion to its concentration, 79% of the 750 mmHg is caused by nitrogen, that is around 600 mmHg, and 21% is by oxygen, that is about 160 mm of Hg. Thus, the partial pressure of nitrogen in the mixture is 600 mm and the partial pressure of oxygen is 160 mm Hg. The total pressure is 760 mm Hg, the sum of the individual of partial gases. The partial pressure is designated by the symbols P, for example, partial pressure of oxygen and partial pressure of carbon dioxide. Bulk flow. Gas from atmosphere enters the airways starting from nostril down to the alveoli by bulk flow. The driving force of this bulk flow is pressure gradient, which is created due to the difference in barometric pressure, the pressure at the mouth and the alveolar pressure. Exchange of gases between alveoli and the capillary blood occurs across the alveolar capillary membrane by diffusion in response to partial pressure gradients of the gases. For example, oxygen uptake from alveoli into the pulmonary capillary blood occurs due to the partial pressure gradient of oxygen across alveolar capillary membrane. Factors that contributing to gas exchanges. The gas uptake from alveoli is determined by four factors. One is diffusion properties of alveolar capillary membrane, partial pressure gradient for the gas, pulmonary capillary blood flow, and diffusing capacity of the gas through the membrane. Coming to alveolar capillary membrane is also called as respiratory membrane, forms the blood-gas interface that separates the blood in the pulmonary capillaries from the gases in the alveoli. The diffusion of gases between alveolar air and pulmonary capillary blood takes place through alveolar capillary membrane. The alveolar capillary membrane is exceedingly thin and is mainly composed by alveolar epithelium, interstitial fluid layer, and capillary endothelium. As the blood perfuses the alveolar capillaries and air ventilates the alveoli, oxygen and carbon dioxide move across the blood gas interface by diffusion. Layers of alveolar capillary membrane. From the interior of the alveoli to the capillary blood, the alveolar capillary interface consists of 6 layers. However, oxygen from the hemoglobin molecule in the red cell of the pulmonary capillaries to enter into alveolar lumen, or the transport of in reverse direction passes through the 10 layers. So this is the diagram of alveolar capillary membrane, which is showing different layers. The surfactant layer, the alveolar epithelial cell, the and then the basement membrane, interstitium, basement membrane of the capillary endothelium, endothelial cells, then the plasma, red cell membrane, intraerythrocyte fluid, and then the hemoglobin molecule. Okay, so these are the layers. Alveolar surfactant, the layer of alveolar epithelial cells, basement membrane of the alveolar epithelium, thin layer of interstitial fluid, basement membrane of the capillary endothelium, layer of capillary endothelial cells, plasma, red cell membrane, intraerythrocyte fluid, and hemoglobin molecules. The thickness of the alveolar capillary membrane is normally 0.2 to 0.5 microns. The thinness of the membrane allows easy diffusion of gases through it. Factors affecting diffusion of these gases. Diffusion of gases through alveolar capillary membrane depends mainly on the 6 factors: difference in the partial pressure of the gas on the both the side of the membrane, that is partial pressure gradient for the gas, then diffusing capacity of the membrane for the gas, then surface area of the membrane. Surface area for diffusion uh, decreases in conditions like emphysema and increases in conditions in which there is more opening of number of capillaries as it occurs in exercise. It also depends on solubility of the gas. Solubility of the gas in the membrane is an important factor for diffusion. For example, carbon dioxide being more soluble diffuses more easily. Thickness of the membrane is inversely proportional to the thickness. The alveolar capillary membrane, when thickness is doubled, the diffusion is halted. That is, when thickness increases 2 times, the diffusion is reduced to half. The molecular weight of the gas. The diffusion is inversely proportional to the molecular weight of the gas. Thus, gas with a smaller molecule diffuses easily through the membrane. Though the alveolar capillary membrane is thin and does not interfere with the gas exchange, diffusion is disturbed in disease conditions like due to some membrane pathology. So this is called as alveolar capillary obstruction syndrome. So this syndrome occurs in 2 important types of defects. One is thickening of the alveolar capillary membrane, as seen in the diffuse interstitial fibrosis, or like in asbestosis, uh, or increased in case of increased distance between the alveolar and capillary membrane due to the interstitial edema, as seen in heart failure, etc. In alveolar capillary obstruction syndrome, diffusion of oxygen is decreased, but not carbon dioxide. Though the both oxygen and carbon dioxide are highly soluble in lipids, carbon dioxide is 20 times more soluble in water than oxygen. Therefore, in conditions like interstitial edema, in which more fluid accumulates in the space between the alveolar capillary membrane, diffusion of carbon dioxide is not hampered. Thus, in alveolar capillary obstruction syndrome, hypoxemia develops without significant change in the partial pressure of carbon dioxide. Diffusion gradient. The diffusion of gases depends on the difference of partial pressure of the individual gases across the alveolar capillary membrane. So this is also called as diffusion gradient for the gas. For example, oxygen diffuses easily across the membrane because of a greater difference in partial pressure of oxygen between alveoli and the pulmonary capillaries. Normally, the diffusion gradient for oxygen is about 60 mm of Hg, so which is the difference between uh, the partial pressure for oxygen of the alveolar air, that is 160 mm, and the arterial blood, that is around 100 mm Hg. The diffusion gradient for carbon dioxide across the alveolar capillary membrane is about 6 mm Hg, so which is much lower than that of oxygen. The gases that are dissolved in the liquid when they are exposed to such liquids like plasma. In this dissolved state, in the liquid, gases exert partial pressure. So Henry's law states that the amount of gas dissolved in a liquid at given temperature is directly proportional to the partial pressure and the solubility of the gas. Whereas Fick's law explains the diffusion of gases across the alveolar capillary membrane, it states that the volume of gas diffusing per minute across the membrane is directly proportional to the membrane surface area, the diffusion coefficient of the gas, and the partial pressure uh, difference of the gas, and inversely proportional to the membrane thickness. So here are table showing the partial pressure of oxygen, carbon dioxide, nitrogen in inspired air, expired air, alveolar air, venous blood, arterial blood, and the capillary blood. The diffusion coefficient. The diffusion coefficient of a gas is directly proportional to its solubility and inversely proportional to the square root of its molecular weight. Therefore, highly soluble molecule or a smaller molecule diffuses rapidly. For example, the diffusion coefficient of carbon dioxide in aqueous solution is about 20 times greater than that of oxygen because of its higher solubility, even though it is a larger molecule than oxygen. Capillary blood flow. The flow of the blood in the pulmonary capillary significantly influences the oxygen uptake. Normally, the transit time, the time taken by the red cells to pass through the capillary, is approximately 0.75 seconds, during which the gas tension in the blood equilibrates with the gas tension in the alveoli. Uptake of nitric oxide is flow limited. So, with the increase in the cardiac output, blood flow through the pulmonary capillaries increases that decrease the transit time. For example, nitrous oxide, an anesthetic gas, easily diffuses across the alveolar capillary membrane and equilibrates in zero point 0.1 second. Thus, only way to increase the transfer of nitrous oxide from the alveolar air into the blood is by increasing the blood flow. The amount of nitric oxide uh, or nitrous oxide that can be taken up is entirely limited by the blood flow, not by diffusion of the gases. Therefore, uptake of nitrous oxide is flow limited. Carbon monoxide transfer is diffusion limited. In the other hand, diffusion of carbon monoxide is different. Carbon monoxide is, carbon monoxide also readily diffuses across the alveolar capillary membrane, but due to its high affinity for the hemoglobin, it rapidly binds to the hemoglobin. This decreases the partial pressures of carbon monoxide in blood, for which the equilibrium for CO across the alveolar capillary membrane is never reached in zero point 0.7 seconds, that is the transit time. Oxygen uptake is flow limited. The capillary oxygen tension equilibrates with the alveolar oxygen tension well within transit time, normally in one third of the available time, that is in zero point 0.3 seconds. Thus, a wide safety margin is available for oxygen to ensure that the end capillary uh, PO2 is fully equilibrated with the alveolar PO2. During severe exercise, though the transit time is reduced, but still the time is adequate to fully oxygenate the blood. Though oxygen binds with hemoglobin less avidly than carbon monoxide, oxygen equilibrates fast. Coming to diffusing capacity, the ability of the respiratory membrane to exchange a gas between alveoli and the pulmonary blood is expressed as a diffusing capacity of the respiratory membrane. DC is defined as a that volume of a gas that will diffuse through the membrane each minute for a partial pressure difference of 1 mmHg. The diffusing capacity provides the measure of rate of gas transfer in the lungs as per their partial pressure gradient. How do you measure diffusion capacity? The carbon monoxide is used to determine the lung diffusing capacity because of the several advantages. Its uptake is limited by diffusion and not by blood flow, so there is essentially no carbon monoxide in the venous blood. The affinity of carbon monoxide uh, for hemoglobin is 210 times greater than that of oxygen, which causes the partial pressure of carbon monoxide to remain essentially zero in the pulmonary capillaries. To measure the diffusing capacity with the carbon monoxide, the equation is diffusing capacity is equal to VCO divided by PaCO, where VCO is a carbon monoxide uptake in ml per minute and P alveolar carbon monoxide is the alveolar partial pressure of carbon monoxide. The most common technique for making this measurement is called as single breath test. Factors that are affecting the diffusion capacity. The hemoglobin and capillary blood volume affect the lung diffusing capacity. The diffusing capacity not only depends on the diffusion properties of alveolar capillary membrane but also on hematocrit and capillary blood volume. A decrease in either the hematocrit or capillary blood volume decreases the diffusing capacity. So this is in brief about the diffusing capacity of the gas. Thank you.